This was Moonlight and Jasmine by Phillip Wesley. The next piece is a piece about my interpretations of three constellations, Orion, or actually I'm going to start with Cassiopeia. Cassiopeia, actually, instead of Cassiopeia's chair, I see a seal. Instead of Orion the hunter, I see a kite. And instead of Leo the lion, I see a little teapot. Here we go. Racing Against the Sunset with Phillip Wesley.
Oops.
And I can end there.
Thank you very much, Kim. Can you hear me?
I guess I ran out of time to get on my harp.
Uh, yeah, I think Doug should be starting things
Yeah.
in a minute or so. I can't see him on this.
Be right back.
You just want to do the introduction?
I'm not sure who all is on. No.
I'm here,
Well,
but there's no one from I don't think there's anyone on the ground there. I think they were coming over.
We can
okay.
get started with the announcements. Why don't you just do the introduction and get started with the announcements?
Okay. Well, everybody, we were thinking we had everything under control, and it looks like we had a glitch in the transition. But welcome anyway to the September meeting of Orange County Astronomers. I am your current president. I'm Barbara Toy. Doug Millar is moderating things on the ground, and we have a great program lined up for you. So without more ado, let me turn it over to Kyle Graham to give us the club announcements for the month.
All right, I think they just came in from on the ground, so I think, are we good to go?
Yeah.
Okay. All right, everyone. Welcome to the September meeting, and I do apologize if it's quite loud where I am. We're having some thunderstorms roll through, so don't mind the random noises. Welcome new members. You guys can either pick up your name badges on the whiteboard in the auditorium. They normally take about a month to get there, and if that's inconvenient for you, then they'll be mailed to you. Star parties. The next ANZA Star Party is September 16th. Orange County wants to be announced. Special interest group meetings. We have Astrophysics Special Interest Group September 15th at the Heritage Museum. Beginners classes on October 6th online, and the board meeting is also online September 24th. You can see all the information about these events on the OC Astronomers website. Jeff Gray is our Outreach Events Program Coordinator. You can contact Jeff at the email below, outreach@ocastronomers.org. Coffee stand is open as you walked in. If you're in person attending the meeting, feel free to grab coffee, donuts, water. They'll be there throughout the meeting. Please remember about the Adopt Scope program. You can see the current inventory along with the sample adoption agreement on the website as shown here. Dave Fisher is the Serious Astronomer newsletter editor. If you have any items of interest that you think would be interesting for other club members to read about in the newsletter, please send him those items at newsletter@ocastronomers.org, and he will review those items. Again, just a reminder that everyone is mailed the newsletter. If you wish to opt out of receiving a mailed copy, please send an email to Charlie. But remember that everyone receives a mailed copy unless you opt out. Please remember to keep weeds clear at ANZA. Always just a regular reminder. Are they here tonight? I don't see them. The 2023 annular eclipse is coming up next month, October 14th. I believe that's a Saturday. Here's kind of a map that's showing the path of where the annular eclipse will be fully visible. And there's a link for more information about that. Just want to make sure that was on everyone's radar. And next up will be John Garrett doing the What's Up presentation, followed by Shane Larson, our featured speaker for the evening. Thank you.
Great job, Kyle. Thank you very much. And now, John Garrett, every month this gets more complicated, and I have to get out of the way while John and the speaker work on his computer, which is a Mac instead of a PC, to get What's Up, so that then later we can have the meeting up. Barb, do you want to say hello while you're there? No, our president has been sick for several days and she's not here in person, but online. You ready, John?
I already did
Helen,
the
can we-
greeting. You missed it.
Okay. Helen, can you turn the lights down a little bit? Angels from afar will dim the lights. It does matter. Okay, John, I'm so glad to have you here. You do such a great job, and we really appreciate your work. And it's more than I can do, and I appreciate really watching it. So here you go.
Thank you. That's really nice to say, and I really do appreciate the opportunity to share photos. I don't really have many other places to share them, but I also find that doing these presentations really motivates me to get out there and get the images. So I'm really happy to be able to do that. I think, oh, we don't think they're seeing this on the online world. So we're going to hold off just a moment, see if we can get it back in. But anyways, I did take a bunch of pictures, mostly this week. Most of the pictures I took this week were with my 24mm cheap camera lens. So I wanted to have a bunch of fresh astronomy pictures for tonight. And then, and I'll just show you where I started. First of all, this week started with some very exciting news that there was a comet in the morning sky. And if you've been looking online, you might see it's a very photogenic comet. I didn't actually have that much luck, but I did get out yesterday morning and I photographed the area that I thought the comet would be in. And in this picture, you can see the planet Venus and the constellation Cancer. And I'd hoped that the comet would have just shown up, obviously, in my camera, but it wasn't so clear there. Now, here's the sickle of Leo. And when I zoomed in, I had to put in all these stars from my map of Leo to figure out if there's anyone there that doesn't belong. And that little white dot that you see right there is the comet. That one didn't belong. So it's a photogenic comet for other people, but for me, just give you an idea of what it's like. This comet was not really delivering for me. But anyway, Friday morning today, it would have been here, and I was hoping to get a picture, but it didn't happen. But tomorrow morning, it's going to be about there. So it gives you an idea about where that comet is and whether you want to try to get it this weekend. But maybe tomorrow morning might be your last opportunity. Of course, my horizon had some mountains on it, so you can get an idea of how much space. There isn't much space there, but you might be able to get that. I took these pictures around 5 o'clock in the morning, so I think you have another hour of a little bit of wiggle room, but it is going to be a challenge, but to definitely try it. And as far as I can tell, I don't think it's going to be back in the northern hemisphere after it whips around the sun. I think it's going to be visible in the southern hemisphere, but not to us in the north. Anyway, that was kind of exciting. But if you're up in the morning, you see Venus. If you look about 90 degrees upward from Venus in the morning, you'll come to Jupiter, which is high overhead. And here you can see Jupiter with Pleiades and Taurus. And also in my picture, I don't know if you can see it, but there's a little green dot that is the planet Uranus. So planet Uranus is very close to the Pleiades and Jupiter. So it's not too hard to find if you're interested in hunting that one down. In fact, most of us, the first time we saw Saturn in a telescope, that was like a very big step for us in the hobby of astronomy, because, you know, a lot of us say, well, it looks like a cartoon. We can't believe it's really real and all that. And I had that reaction too, but I really felt competent as a modern amateur astronomer the first time I actually saw Uranus and could identify it as clearly a tiny disk, because I realized then I was looking at something that most of humanity has never seen. So by all means, give Uranus a look. Anyway, if you do wait about an hour after those last pictures of what I tried to get of the comet, you'll see Venus getting higher. So there is some darkness to work with if trying to get that comet tomorrow. Anyway, a little tour of the evening sky. This week, I was able to find this is sort of a parenthetical. As I show the pictures of the evening sky, I'll also be showing my pictures of some of the deep sky objects. And so just a reminder, whenever I say something like TV 76 or 3-inch telescope, it's that little white telescope on top of this platform that the picture was taken with. And then the larger one is an 8-inch Schmidt Cassegrain. So I usually label that as SET at f6.3. The other one, I usually say TV 76 at f5. Both of them I use a focal reducer for. I don't do any guiding. That's going to be my next step. So far, my goal is whatever photograph I can get within a 30-second or a minute window is usually what I work with. And recently, I've been learning how to stack some of those. And there's a screen capture of the stacking software that I use. So that's all parenthetical as I go into a view from my backyard. Every year, this time of year, I try to take a photograph of this area of sky as sort of my long-term record of the degradation of the night sky due to light pollution. It's not a very pleasant story, but I can still get a view of the Milky Way from my backyard when I tweak the contrast of my photos. But here's looking to the southwest right now this week. And here's the constellation Scorpius, one of my favorites for its shape. And here's the figure that gives it its name. And in Scorpius, a quick review. Here's some bright Messier objects that you may want to look at before they disappear for the year. M4, beautiful globular cluster, and then M6 and 7, very beautiful open clusters that are also good in binoculars. I'm going to go this direction in my photos and come to the constellation Sagittarius. And here's the classic teapot of Sagittarius, and here's the figure that gives it its name. And then this area here, nice little review of things that you might want to see as before they get too low. So these are the brighter objects in the area, several Messier objects. I covered a lot of these last month, so I wasn't want to go into them, but just a reminder, they're out there, still a good chance to see them in the evening. And if you go this way, you'll come to the constellation of Capricornus, the sea goat. I haven't drawn a sea goat yet. I'm still waiting for a suitable reference to go by. But Capricornus, when I see that, you can think of two fairly bright planetary nebula worth hunting down. The Saturn Nebula, NGC 7009, and the Helix Nebula 7293. And Capricornus does rotate up a little bit from the time that I took this picture. So the Helix Nebula does rise higher through this time of year. And here's the Saturn Nebula. This, I think, it was taken with my Schmidt-Cassegrain telescope. And here is the other one, the Helix Nebula. This one was just a single exposure, and with my small telescope to just give you an idea of how big it is, and it's fairly bright object. And then with a little stacking, of course, it becomes much brighter and much nicer. So this time of year, I'm hoping to revisit those, get some better pictures of them now that my abilities, I hope, are getting a little better. And so they may be things you want to look at or try to photograph initially or do some nice projects with. So if I go a little bit this way, you're going to come to Saturn. And Saturn, I did get a chance to look at Saturn this week, and it's you can see its rings are definitely flattening out from last year, but you can still see some separation around the planet there. And if I go up this way, I'm going to follow the Milky Way. It sits up pretty much right over the sky, right over the ceiling of our sky this time of year in the early evening. So I'm going to go this way and end up in the constellation Scutum, the Shield. And there is a lot of stuff there we're seeing. There's the M24 star cloud, which I showed in a previous image, but then right above it, the M17 and 16 nebulas and the M11, a very stunning open cluster that's good in at several powers of magnification in telescopes. So here's the M16 nebula, and then the M17. And then M11. And this one really, once you put a big, an eyepiece on your scope, it really pops nicely. And then going up a little farther, following the Milky Way, we come to the constellation Aquila, the eagle. And I'm not really sure how the eagle is supposed to be drawn, but that's lately how I'm coming up with it. And then Delphinius, just off to the side there. And if we're going, I'm going to come back to this area because this is starting to become my favorite area of the sky right now. But I'm going to go just a little farther, finish the tour, and I'm going to come back to that. So we go a little farther above Delphinius and the Aquila. We come to the coat hanger constellation, or the constellation, but asterism. And then a little farther, we come into the constellation of Cygnus the Swan. So what I've just done with my photos is I've looked southeast, gone a little bit this way, then back up and followed the Milky Way until it comes to my Palo Verde tree, which interferes with the rest of the view. But the Palo Verde is there to block the street light, and it works out pretty well. So I'm going to show a little of my favorite objects in this area. Looking at Aquila, this photo I took some time ago at a much darker location than my front yard, and there's just a number of interesting things here. For example, the star clusters up there at the top of the screen, NGC 6633 and IC 4756. Can see those. It's kind of faint, but you can see them in binoculars. And then also these star clusters, the NGC 6709 and 6738. So here's ones that I captured this week just to show tonight. So here's 6633 and 4756. These are in my small telescope. And then a little tighter cluster there. You can see that in the same telescope. And then a very loose cluster. I was even wondering if I got the right one, but I think that's it. And then, of course, M71, a globular cluster in that area. And then there's Bernard's E, which is right near the star Terra Z. And so it's a dark nebula. And so back to here. And of these objects, there's other kinds, the planetary nebula, which are kind of my favorite. I love hunting down planetary nebula, mainly because they just show up on my camera. When I've taken the picture, I've just a regular digital camera stuck on the back of my telescope. And a lot of them just show up as these tiny little green dots. And I just find that fun, since none of the stars look green. Just to have a little green dot on the camera is just exciting for me. But here's a few of those green dots. This one in my Schmidt-Cassegrain. And this one also in the Schmidt-Cassegrain that I started to stack. So these are the ones that I'm really eager to come back to and get some more time and get a little better and see what they really look like when I've done a better job of them. And then there's that tiny little green dot right there in the middle. Hope you can see that. And then, of course, this one has a certain size to it. It's always impressive that you've got several planetary nebula in this region that have noticeable size to them, because a lot of them with the equipment that I use, I can't get very much a detail, but that's really exciting that you can get some detail on these. And then there's one more tiny green dot. I hope you can see that almost dead center. Oh yeah, and another one, 6804 and 6804 stacked. Still have some color problems with it, but you can kind of get an idea of the little nebula. And then, of course, M27 shows up pretty nice. And it's a very bright M27. Oh, I wrote M24. That's a mistake. M27, very bright dumbbell nebula. This is a single exposure with my Schmidt-Cassegrain and just tweaking the contrast of the photo. And then here it is with a little stacked version that I've done. Anyway, so that area of the sky is like one of my favorites. And so globular clusters, a few, but a lot of planetary nebula. And then the whole place is actually dark nebula. When you look at it, it's got a lot in there. And going a little farther, we go to Cygnus the Swan, and there's a few favorites here. North American Nebula, M39, M29. I'm not really putting that on as a favorite, but here's the planetary nebula in that area too. So I'm going to show you a few of those real quick. 6905, very near Delphinius. This is a very bright one, comes out really nice. This one here, a little globular cluster, NGC 7006. And I think you can see it. I can barely see it on this screen, but there's a very faint but large planetary nebula there. And then a very bright one, also called the blinking nebula. I think it's what's called, because it's just usually bright enough that when you look at it through a medium-sized scope, it tends to blink in and out of our vision. But I noticed that in like a larger scope, like an 11, it definitely stays put. And then I think this one is a green dot. Yes, a green dot right there in the middle. And another little green smudge. This one has a little bit of size to it. And then another little green smudge, again, planetary nebula, stuff that I'm excited about. And then, of course, the Veil Nebula in its two parts, being two halves of a supernova remnant. That's also in Cygnus. So again, there's just the Cygnus, the two large birds essentially in the sky right now are well placed for the evening. The evening comes sooner, noticeably sooner, because it's getting into fall. So it gets dark at a respectable hour. And these things are in a perfect position for sighting them, hunting them down visually, and finding them also, photographically. So thank you. Sharon, give me that opportunity to share all those, and enjoy.
Thank you very much. That's something to remember, that in June and July, the sun goes down pretty late and this makes a short night of observing. And these days, the night is quite a bit longer. So it's worthy to go out and see what you can do. So I guess I'm the de facto impresario, and I'll introduce the speaker. But I don't have anything to say because I thought somebody else was going to do it.
Yes, that somebody else is here,
tell me who you are.
Doug.
Oh, Reza said
Doug,
something.
can you hear me?
Okay. Are you going to do Reza?
Yes, yes.
Okay.
Okay, so I want to first let's thanks John for his great presentation. Thank you very much, John. So let me jump ahead and go ahead and introduce Shane for tonight's speaker. Our tonight's speaker is a research professor of physics at Northwestern University, where he is the associate director of the Center for Interdisciplinary Exploration and Research in Astrophysics. He works in the field of gravitational wave astrophysics, specializing in studies of compact stars, binaries, and the galaxy. He works with both the ground-based LIGO project and future space-based observatory LISA. He was formerly a tenured associate professor of physics at Utah State University. He is an award-winning teacher and a fellow of the American Physical Society. Please join me in welcoming Shane Larson. Shane.
Hey. Thank you, everyone. Thank you, Reza. Thank you, John, for the tour of the night sky. I'm an amateur astronomer as well as a professional astronomer. And so one of the things that I love doing is coming and talking to amateur astronomers, because we get to be nerds and then I get to tell you about what I do for my life anyways. So, but I am going to talk to you tonight about what I do professionally. And I mostly work in gravitational waves. I do a very broad, wide variety of things. But when they ask me to come talk, I usually give you a long list of things I can talk about. It seems you've heard about gravitational waves many times, so I'm not going to talk about stuff you've likely heard about. I'm going to talk about, not going to talk about LIGO, probably not going to talk about pulsar timing. If you want to ask me questions about it, I can. I am going to talk to you about LISA. So let me share my screen here. And I got to get back to Zoom over here. So desktop 2, I will share that, and I will go back to here, and I will play, and you should be able to see my screen.
Yes, all
like
good.
There. Okay.
And are you sharing sound also?
Okay. Okay. So gravitational waves are a more or less brand new kind of astronomy. It's something that we have thought about and speculated about for 100 years. Einstein himself was the person who thought about this. He died not knowing if it was possible. We figured out it was possible very shortly after Einstein's death, and then we've spent the last 60 or 70 years actually turning it into reality. And so what I'm going to tell you about tonight is a little bit of that story. Okay, so my email address is not there. It's normally there. Okay, my email address is s.larson, Larson, at northwestern.edu. And I normally put it there because we'll answer questions tonight if you have them. But as most of you know, about 2 weeks from now in the middle of the night, you'll wake up, you'll have some question you wished you had asked me. Most of you know at this point, if you wake up your significant other at 2 a.m. to talk about astrophysics, they get mad at you. So you email me and I'll do my best. I'll send you some answers, point you at something you can read, YouTube videos, something to help answer your questions, okay? That's my blog there, rightscience.wordpress.com. It is a public-facing blog. I've written a lot of stuff there about gravitational waves, a lot about black holes, a lot about astrobiology and SETI and various other things that we worry about. It's really there so my mom knows what I'm doing. So for those of you who are feeling a little uncertain about your science background, it should be accessible, and hopefully you can find some stuff there as well. You can certainly follow me on social media as well. Okay, so I'm going to talk to you about gravitational waves, but specifically in the context of LISA. And we live in an era that really is the beginning of the era of gravitational wave astronomy. This map shows across the globe all of the current efforts that are underway of functioning or near functioning gravitational wave detectors. There are others at various other parts of the gravitational wave spectrum. We'll talk about that in a moment. They're not here. But you'll notice the kind of ones that you've heard about, the LIGO detectors together with Virgo and Kagra. are the ones that are currently online and the ones that you hear all the discoveries of. If you were paying attention this summer, our colleagues at Nanograv, together with the European Pulsar Timing Array and the Parkes Timing Array, made an announcement of the discovery of gravitational waves in their part of the spectrum. You may have remembered from several years ago, there was a possible, now we don't think, detection of the cosmic gravitational wave background using the cosmic microwave background. That experiment is underway again, and they are making measurements, and I expect in the next 5 or 10 years, we will hear a result. But what I'm going to talk to you about is a detector called LISA. Now, LISA is not built yet. It is about to be adopted, as we say. I'll tell you about what that means, but in about 10 years, we will be on orbit. And so what I'm going to tell you about tonight mostly is about LISA, okay? Now, given all of these detectors and all of these different things that we're doing, a common question that we always get is, why do we need all of them? Okay, and so in order to tell that story, I want to appeal to a story some of you may know, a story that we call the parable of the spectrum. It started in 1800 with this guy, William Herschel. In the olden days, none of us in here remember these olden days, but in those olden days, we didn't know as much about the world as we know today. In particular, we didn't know anything at all about the nature of light. We knew that it could behave like waves. We knew it could behave like particles. There were still lots of arguments. We knew that you could break it into a spectrum, but all of the things that you're taught in fundamental chemistry and physics about light, we didn't know. And so gentlemen scientists like William Herschel were trying to understand what are the physical properties of light. And so Herschel did this very famous experiment where he took a sunbeam, he broke it apart into its constituent spectrum using a prism, and then he took thermometers and he put them in each of the different color bands in the spectrum. And his goal was to try and understand if all the different colors of light in the spectrum were the same or different. Did some of them have more energy than others, as witnessed by changing the temperature? And quite by accident one day, he was, rather sloppy on his lab desktop, like many of us are, and he accidentally left a thermometer laying next to the spectrum that he was projecting, well outside of the colors. And he noticed that the thermometer got hotter. He had accidentally laid a thermometer in the region of the spectrum that today you and I call infrared light. He had quite by accident discovered light that our eyes cannot see. Okay, so today we know this is just part of what we call the electromagnetic spectrum. You and I can see visible light, but the spectrum itself is much, much larger. Okay, it extends to, if we think about light in terms of a wavelength, okay, so wavelength is a number that we use to precisely define what color we're talking about. As physicists and astronomers and chemists, we like numbers better than words. If I say red, how do you know what I'm talking about? If I say 660 nanometers, you know exactly what I'm talking about. Okay, so this wavelength number that we use gets shorter as you go to the left on this figure, and it gets longer as you go to the right on this figure. There are helpful familiar objects here to show you roughly what the size of the wavelength is. If we're talking about radio waves, they are extremely long wavelengths. They can be the size of buildings. Okay, they can be shorter than that. In particular, they can be the length of the radio antenna on your car. For those of us who have old cars with radio antennas on them. Okay, not all of us do anymore. Microwaves are kind of, the size of bugs. Okay, infrared waves, the kind that Herschel discovered, are about the size of the point of a needle. Visible light is about the size of bacteria. Ultraviolet light's molecules, X-rays are the size of atoms, and gamma rays are the size of atomic nuclei. Now, they figured this out because Herschel started this in the 1800s, and it took until the early 1900s to figure it all out, okay? But it took astronomers even longer to figure out it was useful. And the thing we know today is that if I use any wavelength in the electromagnetic spectrum, there's something interesting to discover about the cosmos. This is a series of pictures of the MICE, the antenna, two colliding galaxies that you can see in your amateur telescope. But I pointed these in particular because we'll come back to the question of colliding galaxies in a little while. But if you look at them in optical, this is the way they would look through the kinds of photographs that John was just showing us. They look like you expect galaxies to look. They have kind of yellowish and reddish cores. They have bluish outer areas. They have long diffuse regions. In the case of the MICE here, these are tails where stars that are being left behind by the collision are streaming through space. But if I look in different colors of light, in particular in light that your eye can't see, from X-rays all the way to infrared or down into radio, the galaxies look quite different. And the point is, all of those different colors of light point to different kinds of physical phenomena. We can use them to study dust. We can use them to study energetic processes. We can use them to study radioactive molecules. We can use the different kinds of light to tell us things about the far universe that we have no other way of discovering at all. Because you and I and every other human on Earth are confined to be flat-footed here on the Earth. All those things we know about the universe we've discovered right here, flat-footed, but we've learned how to manipulate the information the universe sends us to understand what's going on far away. Okay? So, why am I telling you this? Well, the reason I'm telling you this is I want to talk to you about gravitational waves and why we have all of those different gravitational wave detectors. I'm going to just turn my computer here so I can see my screen from where I've been standing. Okay. Now, this movie is one of my favorite movies that I like to show people of gravitational waves. When you see movies of what gravitational waves are, you very typically see one that looks like ripples on a pond. You go stand out at a pond, you throw a rock in the middle, and you get these spiral ripples spreading out from wherever the rock fell in the pond. And that's useful to remind you what waves are. But this movie is a far better movie for showing you why gravitational waves are useful and interesting for in the context of astronomy. Okay, so there's a few things about this I want you to notice. The first thing is the waves themselves are being generated by masses moving around. Okay, so in particular for this movie, there are two black holes at the center. They are orbiting each other. When the movie restarts, you'll see that. They're orbiting around each other. And as a consequence of the fact that they're moving, that means the gravitational field that they're generating has to be changing with time. And that change in the gravitational field has to propagate from where those black holes are to wherever anything else in the universe experiencing that gravitational field may be. And Einstein taught us that nothing can propagate faster than the speed of light. And so it takes time for that information to propagate from those two black holes to wherever you happen to be sitting in the universe. Now, the other thing about this I want you to notice is that the waves themselves go out in every single direction from the black holes. And that's why this is a far better movie to show you what we mean when we talk about gravitational waves than that ripples in a pond movie. This is why this is useful for doing astronomy. It's just like stars. Stars send light out in every direction. It doesn't matter if you're sitting over there looking at it in the telescope, or you're sitting over there looking in the telescope, or I'm sitting on the other side of the galaxy looking at it in a telescope. We all get light from those stars because the light is shed in every direction. And gravitational waves are the same way. If they weren't shed in every direction from the sources, then they would not be very useful for doing astronomy because we'd have to be in the right place at the right time to see them. But they go in every direction. Now, it's not uniform. You can see, so the ripples that you see here are the intensity or the strength of the gravitational waves. They have definite shape to them, and they have definite size to them. That size is this wavelength that we've been talking about, and we'll come back to that in a moment. But you can see they are very strong going in one direction, less strong in another direction, but that's okay. That's just like looking at the tip of Saturn's rings and knowing what Saturn's doing this year versus next year. By knowing what the strength of the gravitational waves I'm getting, it allows me to know which direction I'm looking in on this movie from, no matter where I'm sitting. Okay, and that tells me about the shape and the size and the tip of the orbit of the black holes. Okay, so the point is, and we'll return to this over and over again, is there's real legitimate astrophysical information encoded in these waves, which is why, as astronomers, we are keen on using them as an additional tool in our toolbox. Okay? Okay, questions about this movie before I move on? You can stew on it, ask me a little later, ask your spouse at 2 a.m. Okay. Okay, so the whole reason I told you the parable is there is a spectrum of gravitational waves, just like there is a spectrum of electromagnetic waves, a spectrum of light. Here I have drawn the gravitational wave frequency scale. One of the beautiful things about gravitational wave astronomers is we all talk in terms of frequency. If you talk to people who study light, half of them use wavelength, half of them use frequency, half of them use energy, half of them use just who knows what, right? And I know all those halves add up to more than one, but that's the way astronomers are, okay? But they use different units. And so depending on what you like, you spend your whole life kind of converting things back and forth. But because gravitational wave astronomy is kind of being created simultaneously across the entire spectrum, we all are using the same units here, okay? In this case, frequency. Now, roughly speaking, the frequency is related to that wavelength. If you take that frequency and you invert it, 1 over the frequency, you get a time, okay? And that time is written across the top there. And roughly speaking, that time is the time scale over which the masses that are making the gravitational waves are moving, okay? So if I want to detect 10 to the -4 hertz waves, 1 over 10 to the -4 is about 10,000 seconds, which is on the order of an hour or a few hours. Okay, so that's orbits of black holes that are going around each other every hour or so. Okay, if I go up here at 100 hertz, 1 over 100, that's 1/100th of a second. That's black holes that are going around each other 100 times a second. Okay, so that's the way to use this scale. Now you'll notice these 4 bars here. These 4 bars are places where we have good, promising, or already working technology for detecting gravitational waves. And this is in stark contrast to electromagnetic astronomy, where we started 400 years ago with optical telescopes, and it took until the 1970s to finally build infrared telescopes. Okay, so the building of technology in electromagnetic astronomy happened very, very slowly over centuries, because it took us a while to discover that it was useful to do that. But in gravitational waves, we're just starting from the ground up, and we're using technology as far across the band as we can. And right now, mostly the game is, you'll see these big gaps here. Mostly the game is figuring out ways to probe those different gaps. Okay, so here's the looking at the cosmic microwave background to detect the cosmic gravitational wave background. This is pulsar timing, looking at the timing of distant pulsars. This was the big announcement this summer. This is LIGO. This is the LIGO Livingston site, which if you've been paying attention for the last 5 or 6 years, you've heard a lot about. And then here in this blue band, this is in space, and this is LISA, which I'm going to tell you about today. Okay, so why are we probing across the whole spectrum? Because people like me, so I'm really a theoretician. That means I think things up on paper, and then I tell my friends with telescopes, go tell me if this is real or not. Okay, we can think up all kinds of things across the spectrum which should exist, which we have really good evidence for they should exist when I look out into the cosmos. Okay, that includes Big Bang gravitational waves, stuff from the creation of the universe, the merging of massive black holes, stars falling into black holes, compact binary stars, binaries merging, stars exploding, all kinds of sources across the entire spectrum. And the largest density of them are up here in the so-called high frequency end. And this is why you're hearing about discoveries from LIGO, and why I'm going to tell you about LISA is there's lots and lots and lots and lots that we would like to discover. Okay? Okay. So this is the spectrum. Okay, and we could have a meeting like this every day, every week for a year, and we wouldn't get through all of it. Okay, so I'm going to blast through the LISA stuff here today and tell you all the stuff about LISA that we can. Okay, so first though, what is LISA? So LISA is exactly, it's an acronym, and the acronym is exactly what it is. It's a laser interferometer space antenna. It's an antenna in space, laser interferometer for detecting gravitational waves. There are 3 individual spacecraft. Each of them is about 2 meters across, about 50 centimeters deep. They have basically 8-inch telescopes. They're F1 off-axis telescopes. They shoot the laser out. The laser goes sailing off to the distant spacecraft. The laser beam comes in the same telescope that's transmitting laser light. And what we do is we time how long it takes the laser light to fly from one spacecraft to the other. Okay, and we do that between all the 3 spacecraft in each of the directions. Sounds easy, right? Well, these spacecraft are 2.5 million kilometers apart. So it takes the laser light 8.5 seconds to get from one to the other. Okay, and we will time them and be able to tell you how accurately those spacecraft are separated to the level of picometers. And all of you are furiously thinking about your high school physics class and your metric prefix table. What is pico? Pico is 10 to the minus 12. 0.11 zeros and a 1. Okay, it's a very small distance. Okay, that's the technology. Okay, but the 3 spacecraft are constantly in motion. So they will follow the Earth in this triangular configuration. They will orbit around the sun. And as they orbit around the sun, they will slowly cartwheel around. And so I'm going to constantly monitor the distance between these 3 spacecraft, shooting lasers back and forth between them as they roll around the sun over the course of a year. Baseline mission's 4 years long. Full extended mission is about 10 years. Okay? Now all of you are like, okay. Okay. Now we have a name for that, right? So we call this picophobia, which is a fear of large negative exponents. Okay. It's not easy. It's hard. It absolutely is hard. Okay. But I go and I do my theory astro stuff and I go tell my experimental colleagues, yeah, you can totally detect gravitational waves from black holes from far away. And they're like, okay, we believe you. And I talk to my laser colleagues and they're like, yeah, we could totally measure picometer distances over 2.5 million kilometers. I'm like, okay, I believe you, right? And so this is kind of part of the story today is it takes an entire army, an entire workforce of really smart people to figure out all that it takes to make something like this work. Okay? So what's all this timing about? Okay, so this is true. This is actually true for any gravitational wave detector. Okay, we're just doing it in space instead of on the ground like for LISA. Okay, and so I'm going to go through this here so you can carry this around in your mind, and then you can think about this when you hear talks about LIGO as well. So if we're going to detect gravitational waves, we're talking about gravity. And what does gravity act on? It acts on masses. Right? So imagine this is a grid of masses. Okay, and I'm going to monitor the location of each of those masses. And if they do anything weird, I'm going to use that as evidence that the gravitational waves have passed by. Okay, so these are movies. And what I want you to do is we're going to do the left one first. Okay, so just stare at this when I play it. And I want you to pay attention to 2 things. Okay, so the first thing is I want you to look at overall what happens to the array of masses that I put down. Okay, because that physical effect, whatever happens to that array, is what I'm going to use as the foundation to build a detector. And then the second thing I want you to do is I want you to pay attention to this mass at the center. That's going to be our reference mass. Those of you who are having flashbacks to physics lab and chemistry lab, you always have a reference, okay? So this is our reference mass. I want you to pay attention to what all the other masses do with respect to that reference mass, okay? Now imagine a gravitational wave back there at the back of the room at the projector, shining through the room and traveling straight through the screen and out through the building, going out through the front here in the direction that you're facing. If that gravitational wave passes through that array of masses, this is what happens to them. Okay? As long as the wave is passing by, there is this constant distortion of the distances between all of the masses in the grid. Okay? Now, those of you who know something about any ham radio folks in the audience? A few of you, okay, yeah, KF7, WOZ, that's me. So you know about polarization, right? So polarization in light and radio waves, really for those of us who do radio, it's about how do you orient your antenna, because that's the direction that the waves are vibrating. Okay, so we can make antennas go this way or we can make antennas go this way. Gravitational waves also have a polarization state. Okay, but you'll see the masses in my antenna, in my grid, are moving in two directions. Okay, so here they're stretching, they're getting farther apart in the vertical direction. When they're compressing, getting closer together in the horizontal direction. And then a half a cycle later, they get farther apart in the horizontal direction and they compress in the vertical direction. And then they just go back and forth. Okay, and it's that back and forth pattern that we're going to exploit to look for gravitational waves. Okay, so if you draw lines in the direction of those back and forth patterns, they make a plus. Okay, mathematical plus shape. So we call this the plus polarization. Okay, do you see that? That's the gravitational wave dance. I want videos of all of you doing it at parties this Saturday. Okay? Okay. There are two polarization states. Look at this one over here. That is the exact same pattern rotated 45 degrees. And this is the second polarization state. We call that cross. It looks like an X. Okay, we call it cross. For those of you who remember your vector calculus, this is like the cross product in vectors. Okay, so that's why we call that one cross. Okay, so the game here is this is what we know gravitational waves do to masses that they are flying past. And it was in 1957 that we finally figured out this is what we should be paying attention to. Okay, so imagine if I were to pick just 3 of those masses in the grid, I could shine lasers back and forth between them and time how long it takes the laser to fly back and forth as those masses are moving around in the gravitational wave pattern. That's the game we're playing. And this is what LIGO does with a right angle one, but we can do the same thing with a triangle with LISA. Okay? And the reason we can measure to those picometer accuracies that I was just telling you about is because we're using light to make the measurement. And the speed of light's constant, and we know exactly what it is, and we can time very accurately how long it takes light to make that journey. Okay? Okay. Questions? How big is what? So I'm going to show you the masses for LISA in a moment. Okay. For LIGO, the masses right now are 40 kilogram cylinders of glass. Okay. Sapphire, I think, actually. So, or the plan is to go to sapphire. So they're about the size of a giant coffee can. Okay. But LISA, they're a little bit smaller. I'll show those in a minute. Yeah, so there are onboard, we have multiple frequency references on board. We stabilize our lasers against them, and I don't know exactly what they use for the reference, but it's it's all optics based. It's all ring stabilized lasers, I think. So, okay, but I'd have to go look because, you know, I'm not one of those guys. So, okay, but that's a good question. We have multiple clocks on board for exactly that purpose. Okay. I saw one other hand. Yes, sir. Why does the center not move? So the point is the center doesn't move is because I picked it as my reference. And what I plotted was the distance from that one to everything else and how it changed. I could have picked any one of the masses as the reference, and it would have sat still if I had done that. It was my 0 point, exactly. Okay, that was a good question. Okay, one more. So the lasers on LISA are 1064 nanometer infrared lasers. Okay, so they are an off-the-shelf, I think they're solid state, they're looking at the solid state LED lasers that we have now. The problem with them is they have to run continuously for 10 years, so lifetime's the game, right? Yeah. So, okay, I think they're N-Pros. I can't remember what company makes N-Pros. So, okay, so someone asked about the LISA mirrors. These are the LISA mirrors, okay? So the LISA mirrors are cubes of gold and platinum, okay? They are about 4 centimeters to a side. They weigh about 2 kilos each, okay? They are highly polished, so they reflect the laser light. And this mirror floats inside the middle of the LISA spacecraft all by itself. And it doesn't touch anything. And the job of the spacecraft is to shield that mirror from everything except gravity. And if gravity makes the mirror go that way, the spacecraft follows the mirror. Okay? Yeah, wild, right? Yeah, it's totally cool. The reason it's gold and platinum is there are magnetic fields in space. And the gold and platinum alloy is chosen to be very, as we say, it has low magnetic susceptibility, so it doesn't couple to those magnetic fields because we don't want anything except gravity to push the cube around. Okay. Now, this is LISA Pathfinder. So this is a mission we launched in 2015, in December of 2015. NASA and ESA doesn't let you build $1.5 billion mission unless you can prove to them that you know how to do what you're going to say you're going to do. Okay, so we had to fly. This is the test mass, the mirror that flew on LISA Pathfinder. We had to fly this test mass and prove that we could monitor its location with lasers to the accuracy needed. If we put 3 of these up there, we could do gravitational wave detection. And we did. We passed with flying colors. Okay. So this is an actual mission that was flown. This is Paul McNamara. He was the PI. This is Carsten Donsman. He's the current leader of the LISA consortium. And this is Stefano Vitali. His team in Italy built the system that monitors the cube. So, okay. Yeah, so it costs like 10 million euros to make one of these. Because, you know, they're machined, they're very exactly weighed, they're very highly polished. And as you might imagine, they don't let people like me and you touch those. Because, you know, we get fingerprints on them, we lick them, you know, whatever, right? Okay, so my friends at Goddard made this one. So this one's an analog. It's exactly the same size and weight as the gold and platinum one, except it's made out of tungsten. Tungsten has almost identical density to the gold and platinum alloy that we use on these cubes. So there in my hand, it shows you the size of the LISA test mass. Okay, tungsten costs about $500 to make that one. Okay. Now, the reason it's in my hand there is because they showed this to me when I was at Goddard, and I was like, oh man, I'm giving a public talk about gravitational waves. Can they take it and show it to them? And they're like, sure, you can do that. So I took it and they're like, just bring it back, you know, blah, blah, blah. So I went and I gave my public lecture. Next time I was at Goddard, they're like, do you have the cube? And I was like, yeah, I have the cube. Here it is. And they're like, what have you been doing with it? I'm like, I've handed this cube to 3,000 people. And they're like, you keep the cube. So I have the cube. Do y'all want to touch the cube? Yeah, you do. Okay. So this is the LISA test mass. I have carried this around with me for like 15 years. And on the flight here, security at O'Hare pulled it out for the first time. And they're like, what the hell is this? So we had a little impromptu LISA lecture at Terminal 1 Security in O'Hare. So yes, I will pass it around. Okay, now, those of you, has any of you played around with tungsten before? Anyone? Okay. So you know tungsten is, you'll see when it gets to you, it's heavy. So the rule is be careful. If you're taking a selfie, balance it on your head or something, just don't hurt yourself. Okay.
It's brittle.
It's brittle also.
Be
Okay.
surprised.
The question that you may ask is, what's the hole in the center? Okay. When you see the tungsten cube, you can't just put it on a rocket and send it into space. You have to clamp it down. You can't just let it rattle around.
Think 30mm teleview eyepiece at night, and you hand it like this.
Yeah, just like you hand around teleview eyepieces. That's right. You have to clamp it down, but then it has to float by itself in the middle. So those little holes are these little fingers that push it out to the middle of its enclosure and lets it go and leaves it floating where it's supposed to. So that's what the little holes in the center are. Okay. Okay. Yes. So that is at ESA's launch site in French Guiana, and I don't know anything about ESA's launch systems. I don't know. So, but if you go to the ESA site, I'm sure they have something about their launch system. They'll tell you all about it. So. Yeah, so that's a good question. So the question is about how do we, as we say, filter things that are noise from things that are signal? How do you tell what's real and what's not? So one of the differences, and we'll talk about this in a moment, for LISA compared to LIGO is that our signals are much, much stronger. So if we were all talking at the beginning of the meeting here, and I was up here whispering like this, it would be very hard for you to tell if it was me or someone else talking, okay? But right now, I'm talking into the microphone and I'm talking much louder, even though they're talking about the cube right there. That's, as we say, high signal to noise ratio. And so it's very obvious you're seeing the signal. And so for lots of the things that we see with LISA, we expect them to be in that regime. Okay, down near the threshold, we have the same problems that the LIGO folks do. And we're learning a lot about how to do it from the way they do it, but we have even bigger problems that they have. But they're not really problems because our problems are astrophysics, not noise. But I'll tell you about that in a moment. So, okay, 2 more and then I'm going to go on. So how are we going to keep the spacecraft following each other? Yeah. So this is a big, we have a big team who works on this. How do you get the spacecraft pointing at each other, and how do they know that they've locked onto the spacecraft and then send their own laser beam back? Okay, anyone here a hunter? Okay, a few of you, right? So when you're shooting rabbits run, and you can't point at the rabbit and get the rabbit, you have to lead the rabbit. And LISA's the same way. So part of the acquisition is knowing where the spacecraft's going to be 8.5 seconds from now when it's traveling at the Earth's orbital speed, which is 30 kilometers a second. So you have to shoot ahead and hit, and the laser beam spreads out. And so you want to hit optimally in the center of the beam. There's all kinds of things. As we have a whole team who's dedicated to those issues, and that's their stuff. And I don't know all the details of how they work it out. So, okay. So, oh, sorry, there's a shadow right there. Yes, right there. One more. Sorry, yeah. So the LISA Pathfinder system, we think, is more or less going to go straight across to the LISA system. The point was to test what the LISA system is going to look like. And there will be changes, right? But by and large, the core of the system, the gravitational reference sensor, is proven technology now. If you go and change it, then NASA will make you go prove that it works again, right? So you don't do that. Okay.
Shane?
Okay, so that's all I'm going to tell you about the mission itself. I really want to talk
Shane?
about. Yes.
Excuse me. This is Barbara Toy. We have a number of people that have been asking questions from the online side.
Sure.
And I don't know if you are aware of those. One was, is LISA in a halo orbit, and what is the period of the threesome?
LISA is not in a halo orbit. LISA is in a solar orbit, and it takes a full year. Basically, it's in the same orbit as the Earth, just behind the Earth. It takes a full year for it to complete a single cartwheel.
Okay. And this one, did the LISA technology reach TRL9, which is, I'm not quite sure what they're referring to, but
Yeah, so this is NASA speak. So NASA has a series of what we call technology readiness levels. So in order to fly, you have to reach TRL6. And then levels above that basically speak to their confidence level. So all of the core LISA sensing technology is at and the maneuvering technology for the spacecraft are at TRL6 or above now.
one of the questions that was what are the approximate speed of the waves, which I think are the referring to the gravitational waves.
Yeah, so one of the predictions of general relativity is that gravitational waves propagate at the speed of light. That has been validated by LIGO in their measurements, and there will be additional experiments we can do with LISA when LISA finally flies. And about half of my PhD thesis was written about that.
Okay, well, I imagine you probably want to get on with your talk,
Okay.
and we're going to have a question and answer session at the end, right?
Yeah, we'll take more at the end, right? Yeah, so, okay.
Thank you.
Okay, no problem. So the gravitational universe, like that spectrum slide I showed you, is very diverse in terms of the number of different phenomena, the different sources, the things that we can probe. And so people always want to know, well, if we've already doing this with LIGO, why do we want to do things with LISA? And it's like that spectrum parable I told you at the beginning. You learn different things when you use different parts of the spectrum. And so the thing you should carry around in your head about the difference between LIGO and LISA is that LIGO is very sensitive to what I'm going to call small systems. And by small, I mean astrophysically small, okay, that are moving very, very fast in fractions of a second. Okay, so small systems are things like 2 neutron stars, 12 kilometers across, colliding. Small systems are stellar massed black holes that are tens of kilometers across, crashing. Small things are the cores of stars exploding, supernovas. Okay, that's what we mean by small. By contrast, LISA will see big systems, big by comparison to LIGO systems, and they will be moving slow, slow by comparison to LIGO systems. So big systems are 2 white dwarf stars going around each other once every 1,000 seconds. That's big and slow as far as gravitational waves are concerned. It is 2 massive black holes going around each other once every 1,000 seconds. They're big. They're black holes that are a substantive size of the solar system. They're going around each other 1,000 times, once every 1,000 seconds. Okay? The stars at the black hole at the center of the Milky Way, when they come in super close to the Sagittarius A star black hole and they whip around it, there are some of them that could potentially get close enough that they would create gravitational waves that are about 1,000 seconds long that LISA could detect. Okay, so this is what we mean by big and slow, small and fast. And this is the primary difference between LIGO and LISA. The phenomena are different, and they are also phenomena which LIGO may see them late in their lives and LISA may see them earlier in their lives. Things will be big and slow, big slow orbits that take 1,000 seconds, but 1,000,000 years from now, they may be going fast because they get closer together. Okay, so this is the kind of thing to carry around in your head. Okay, okay, my cube.
Need some hand sanitizer.
Okay, I have the cube back. That's usually the most important thing because someone always wants to take it home. Okay. Okay, so let's talk about some LISA sources and we'll do this. So this is probably the hardest LISA source to detect, but it's the one that many of us are very keenly interested in. At the centers of most giant galaxies are massive black holes, not unlike the one at the center of our own Milky Way. They can be millions or tens of millions or billions of times the mass of the sun. And occasionally, small objects, in this case, a tiny compact star or black hole, will get very close to that big black hole. And they will engage in what are called zoom whirl orbits. Okay, so you can see this star when it's far from the black hole, it's leisurely zooming around. And when it gets in close to the black hole, it whirls around in these exotic patterns. Okay, now why are we so interested in this? Well, there's astrophysical reasons. How often this occurs tells us something about how often small things fall into black holes and get eaten up, which is part of the story about how big black holes grow. But if you're a relativist, if you're a person who studies gravity, what you're really interested in is this thing in the center the black holes that Einstein predicted in general relativity? And one way to test that is to watch the motion of one of these little particles, which you can see is completely tracing out the volume outside of the black hole. And so the gravitational waves are encoding what does the external gravitational structure of this black hole look like, which we can compare to the predictions of general relativity. Okay, so those of you who are familiar with Earth-based satellites, we do this around the Earth. This is called geodesy. Right now, the most famous geodesy experiment is one called GRACE. GRACE flies around the Earth. We measure GRACE's position very accurately, and it can tell us how the gravitational field of the Earth is changing accurately enough that we can tell when it's the rainy season in the Amazon basin. We can tell that the polar ice caps are getting smaller. Gravity encodes itself. It encodes the properties of the gravitating mass in the gravitational field. And so these EMRIs, extreme mass ratio inspirals, encode the gravitational structure of the black hole. Okay. Now, to someone's earlier question about how will we tell these things away from noise, this is why these are very hard to detect, because one of the masses is big, one of the masses is small, and so the gravitational waves are strong enough to detect, but they're not blaringly bright. Okay, so this will be one of the more challenging things that we look for. Okay. Now, these supermassive black holes, this is something that's just changed in my career as a professional astronomer. We now know that the cores of most galaxies like the Milky Way, most big galaxies, I should say, have a big black hole at the center. Okay, so those of you who read about this, this is related to something called the M-sigma relationship. When you look at the cores of galaxies, the bright bulges, as we say, if there's a big bulge, there's always a big black hole. There are some galaxies that are bulgeless and notably don't have a black hole. M33 is a classic example of this. Triangulum does not have a black hole at the center. Okay, but the Milky Way does, Andromeda does. All the big galaxies that we look at have big black holes at the center. Now, if you look at this array of images, though, this is an image not of single galaxies. This is an image of galaxies colliding. And galaxies do that. Galaxies collide in the universe all the time, because they like to live together in big clusters, just like we do in cities. And we live in cities and crash into each other in our cars all the time. Galaxies are the same way. They live in big clusters and they crash into each other all the time. And when they do, they typically merge and form a new galaxy. Okay, so this is kind of the current paradigm, is that when galaxies merge, this is where big ellipticals come from, things like M87. Okay, and if you look in the center of big ellipticals like M87, they have really freaking big black holes. And the reason is because they came from the mergers of galaxies, and their big black holes eventually had to find each other and become a bigger black hole. And when they do, they make gravitational waves that LISA can detect. And LISA will be able to detect the mergers of big black holes like these all the way to the cosmological horizon. There's no place in the universe that these cannot hide from LISA. Okay? How do you tell them apart? So the question is, how often do they occur? Okay? So for LISA, So they hire people like me to make simulations of this. So Michael Katz, who's a former graduate student of mine, he and I did a big, long simulation to try and predict this. And we get that there are about 5 per year. Okay, but we have colleagues who have also done this, and they get that there are 10,000 per year. Okay, so the question is, how do you resolve that conundrum? And the answer is you fly Lisa, because Lisa's going to tell you what it really is. You don't listen to what people like me and Kat say, right? You fly Lisa. Okay, so Lisa will tell us. But there could be a big number. There could be a big, but there could also be a small number. Okay, yeah, this is what the game's all about. Okay, so let me illustrate for you what this is going to be like. Okay, now the problem with black hole, as astronomers, the problem with black holes, if you're used to looking at the universe with light, the definition of a black hole is it's an object that emits no light, so you can't see it. Okay, but it will emit gravitational waves. And the day I discover gravitational waves with Lisa, if I take that down to the editor at the Los Angeles Times, they're like, go away, kid, you bother us. Because we all grew up in the age of Hubble and now in the age of JWST, and they want pretty pictures. But there aren't pretty pictures that go with gravitational waves. There's artist renditions like this beautiful one I'm showing you right here. Okay, but my data is perfectly understandable. If I steal your iPhone and replace all your Taylor Swift with my gravitational wave signals. The Taylor Swift on your iPhone is just a bunch of wiggles that when it gets pushed out through the headphone jack, gets turned into sound. So if I replace your Taylor Swift with my gravitational wave wiggles, when it pushes it out through your headphone jack, it just turns it into sound. And you can experience the gravitational waves in a way that you're not meant to. Your body does not have a gravitational wave detector in your elbow. That's why we didn't know about gravitational waves till Einstein figured it out. But I can turn them into sound and analog that your body can experience. Okay, so I have 2 identical systems here. A 10 solar mass black hole falling into a 10,000 solar mass black hole. And I'm going to play the gravitational wave data for you. And the only difference is this first one is from a circular orbit, and the second one's from an eccentric, an oval-shaped orbit. And the point here is to illustrate for you that there's real real astrophysical information in the gravitational waves. Okay, so let's listen to these. Okay, first one. Okay, that's called a chirp. Okay, it starts out low, and as it goes on, the frequency gets higher and it gets louder. The reason it gets higher is because as the black holes get closer together, they're orbiting each other faster, and the frequency of the gravitational waves is related to how fast the orbit is. The reason it gets louder is because as they get closer together, the gravitational interaction gets stronger, and so the gravitational waves get stronger. Okay, and so you get that very characteristic chirp. Yes? Right, so this will merge outside of human hearing. Okay, so and so what we've done is this is real time. So this is like the last 30 seconds. And what we've done is we've taken it and we've moved it up several octaves into the audible band for humans. Okay, if I did, I do the same thing for LIGO when we do the LIGO talk, and the LIGO ones are in human auditory range. So we don't even have to do the shift for those. So, okay, that's a good question. Okay, so there's the first one. So that's the
Shane,
chirp. Yes.
The sound didn't come through on the remote.
Oh, that means when we switch presentations, the computer sharing sound did not go. Let's see here. Share computer sound. Okay, how about I play it one more time? You all want? Okay, I just shared the computer sound again. Let's try it again. Okay, can I play that again? Everyone okay? Okay, let's listen to it one more time. Nope, that's the last one. Technology, it makes our life easier, right? Okay, let's try this again. You hear it now, Barbara? Okay. Okay, that's the chirp. Okay, and there could be 5 of those a year. There could be 10,000 of those a year, all starting at different times, ending at different times. Okay. Now, if the orbit's oval shaped, eccentric, as we say, then it sounds a little different. Sounds like your car you had in college, right? Okay. So why does it sound like that? Well, when the orbits are oval shaped, sometimes the black holes are far apart. And when that's happening, the gravitational waves are really weak because the interaction is really weak. But when they get close together, the gravitationals get strong and you hear that pop. And then they're far apart and they're close and you hear a pop. Far pop, far pop, far pop. Gravitational waves tend to make the orbits more circular. So the pops get closer together and closer together because it's getting more and more circular. And eventually it sounds almost exactly like the first one. Okay. So that's the game. And so the job of people like me, we spend our days simulating signals like this and handing it to our buddies in the control room at LISA. And they're like, oh, go look for this, go look for this, go look for this. Okay. And we just slide all the data through computers looking for all the possible signals we think there may be. Okay. Yeah, that's a good question. Yeah, so what you're hearing, so the question is there some Doppler effect here that we have to worry about? So for these, the gravitational waves are coming from the orbit itself. So the individual black holes, as they're moving around, are not doing anything to the gravitational waves. But if the whole system, if the orbit was moving away or towards us, there would be a Doppler shift. Most of these sources are at cosmological distances, so they're cosmologically redshifted, which looks like a Doppler shift, and we have to account for that when we look for them in the data. Okay. 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 So the last few minutes here, let me tell you what my current group actually works on, and that is the Milky Way itself. Okay. So this is a picture I took of the Milky Way in the Pando Forest in central Utah. Anyone been to the Pando Forest? Anybody? Okay. It is an aspen grove that is 80,000 years old, right? So it's awesome to stand out there with your telescope and observe it at night. It's like, this has been this way for 1,000,000 nights, right? It's very cool. Okay, so here's the Milky Way. So the Milky Way is about 400 billion stars. Most of them are like our sun. They're very ordinary. Roughly half of all the stars in the Milky Way are in binaries. If you sit down and you do a back of the envelope calculation, you can convince yourself that over time, all of those binary stars like the sun will eventually die. They will become white dwarfs and they will become binary white dwarfs. And so this is what my group studies, is we study the gravitational waves from dead white dwarfs that are orbiting each other in the Milky Way. And so it's just like a planet going around the sun very slow. The difference is the White dwarfs are very close together, and so they go around each other once every 1,000 seconds or so. There will be some 10 to 50 million white dwarf binaries in the Milky Way in the LISA spectrum. Okay, and to an earlier question that was asked, how do we tell all that stuff apart? Okay, and that's the game. That's the problem. Okay, so the way we normally describe this to people is we describe it as a lunchroom or a cocktail party problem. You go, you hang out with all your amateur astronomy buddies. We're all hanging out, telling stories about late nights with the Messier objects and our latest equipment. And it's just a hubbub of information. And everyone's talking the same language, but you can't make out any individual conversations because everyone's talking at the same time. Every one of these white dwarfs is emitting gravitational waves at the same time. But despite that fact, you can hear your friends who are close to you. We'll be able to hear the white dwarfs that are close to us. And you can hear the people who are across the room and who are really loud and excited about their new panoptic eyepiece they bought. Okay, and the same thing, we will hear the very loud white dwarfs, even if they're completely on the other side of the galaxy. But the confusion, as we call it, the confusion foreground itself, also has astrophysical information in it. From the amount of noise in the cocktail party problem, I can tell you roughly how many people are in the room. I can tell you, is there some big event like an annular eclipse or something about to happen by the general level of excitement in the room, right? The same game applies here. From the confusion itself, I can tell you about the size of the Milky Way. I can tell you about the shape of the Milky Way. I can tell you how old the population is and what different kinds of white dwarfs are in it based on the shape of the noise. So there's true astrophysical information in that as well. But let me just tell you about the bright ones, because those are the ones that we think about the most. So this is a movie flying out from the sun. As we recede from the sun, what you will see appearing are the individual systems from one of our galactic simulations. This is what we do in my group. We simulate the stellar graveyard of the Milky Way. Of the bright systems, the 10 to 50,000 bright systems that will be individually resolvable to LISA. Okay, so as we recede from the sun, you will see them start to pop out. Okay, you will see there are some black ones. Okay, those bright black ones are ones that are already known. Most of them are observable to amateurs. In the colored remains, you'll see the purple ones. That's from a study we did about 8 or 9 years ago of ones that are accessible to small telescopes, kind of meter class telescopes or smaller, and LISA at the same time. And then all of the red ones are the ones that are only observable in gravitational waves. And there's probably more of these red ones if you can get time on the 30-meter telescope or James Webb or something like that. Okay, but for telescopes that you and I have access to, university telescopes, amateur telescopes, these purple ones are the ones. Okay, so what you'll notice as that movie plays is they're found throughout the entire galaxy. So even if I'm not just looking at all the 10 million that I can't separate, if I'm just looking at the resolved bright ones, we still will get information about the Milky Way. We can tell there's a bulge, we can tell the size of the disk, we can tell what we could call the scale height, the thickness of the disk, which helps us learn about the stellar evolutionary history of the Milky Way. Okay, so this is what my group does. We have our own code called Cosmic that basically simulates stellar populations and creates stellar graveyard Milky Ways like this one. Okay. Now, the advantage of doing this as a theoretician before LISA flies is we can say, what possibly might we discover about the Milky Way? And one of the things we don't know about the Milky Way is exactly what its structure is, because we live down in the middle of it, right? So here are two different galactic simulations. We call this the thin simulation and the fat simulation. Okay, and you can see when it's edge on that the two of them have very different profiles based on the locations of the individual gravitational wave sources. This is something that's very difficult to do with stars because there are 400 billion stars and you can't measure their distances accurately. But for a wide number of these sources, we will get their three-dimensional positions, and there are few enough of them strewn throughout the entire galaxy that we can get a picture of what the shape of the galaxy really is. Okay? Okay. So that's what my group does. But let me return to this question of how do we tell it all apart? The difference between LIGO and LISA is we're not going to sit around with LISA waiting for things to happen. Things are going to be on all the time. The problem with LISA is not knowing how to tell if there's a signal. It's how to separate the signals apart from each other. So this is an auditory simulation. So my colleagues at the AEI in Germany made this for me. This is compressed into the length of time here that you're going to listen to it, a year of LISA data that has white dwarf binaries and emeries and massive black holes all together. This is an idealization of what the entire LISA data stream converted into sound might be like. And you can put this on your playlist. You can't get it on Spotify, but if you use iTunes, that's what I do. You can put it on your computer and it'll just spin up, you know, play some Elton John, play some Taylor Swift, play the LISA data, right? Back and forth. Your teenager will roll your eyes at you. You'll be like, honey, it's the symphony of the universe. Okay. But this is it. This is what we're trying to do. And 10 years from now, this is what the reality is going to be. Okay. So this is what it sounds like. Okay, make it louder. That's an emery. Or sorry, a supermassive black hole. Okay, that's all those individual binaries, that little buzzing, right? That's all those individual binaries. Okay, so this is what the game's going to be. There's always going to be signal. There's always going to be data. 10 minutes after we turn LISA on, we're going to know what it looks like. Sorry, what it sounds like, what the gravitational wave of the galaxies look like, right? There's no verbs for observing a gravitational wave, okay? But we will see it. Yeah, so the sound over the course of a year, the sound is modulated. There's another black hole. The sound is modulated in amplitude and in frequency from LISA moving around. So if you and I were to make a plot of this, you would see this big amplitude modulation envelope, right? So it kind of gets louder and quieter depending on where LISA's pointing towards the galaxy. Yeah, it's two stars going around each other once every 1,000 seconds, right? Mm-hmm. Yeah, because when those gravitational waves come through, it makes the cubes do this, right? Yeah. Okay. So that's the story. Okay. This is my group. Okay. I have a big group of students. I have a couple of high school students. I have several master's students. Natalie's a master. Peggy was a master's student. She's a PhD student. These three are my most recent 3 PhD students. Katie Brevik's now just starting a professor at Carnegie Mellon. Michael Katz is starting at NASA Marshall. And Lindsay DeMarkey is currently at Congress trying to teach Congress about science. So those are my most recent PhDs. Several of these others are master's students. Lots of them are PhD students. I have a couple of high school students in my group as well right now. So you can't do all the things that I've told you about without lots and lots of people. Science in the modern era, especially modern astronomy, any modern astronomy, is not done by individual people at the eyepiece anymore. It takes huge teams of people to build the equipment, people to build the computer simulations, people to do the analysis to understand the data. And it's true in individual groups, but it's also true in the big collaborations themselves. And LIGO and LISA, for all the stories that you hear and all the press conferences that you see people like me standing up in front of the cameras all the time, but there are thousands and thousands of people behind the scenes. And that includes computer programmers, it includes our administrative assistants, it includes the welders who built the beam tubes at LIGO, the guys who haul the rockets around at Kennedy Space Center. All of them make these missions happen. And so without all of these people, we really couldn't do the science that I've just told you about. Okay, so it's worth bearing that in mind anytime you see someone like me talking to someone like all of y'all. So I always like to leave you with a few things to go read on your own. There are not very many good public level books about gravitational waves yet. I promise I'll finish mine someday. But the ones that I can point you at are the three best ones are probably these. So some of you may have read this one. This is by Marcia Bartusiak. She's an excellent science writer. Her most recent book is called The Day We Discovered the Universe. Some of you may know in October is the 100th anniversary of Hubble's discovery of the distance to the Andromeda Galaxy. That's what The Day We Discovered the Universe is about. Einstein's Unfinished Symphony, however, is about the building of LIGO. Okay, so there are two editions of this book. If you get the second edition, she wrote the second edition after the discovery. And so there's a chapter in there about the discovery. You can see she won a science writing award about that. Brian Clegg is really a very good public science author. He wrote this it's a nice little short book about gravitational waves, about how we build detectors and what gravitational waves are all about. And then this book over here by Kip, many of you may know Kip. He's here, he's emeritus now at Caltech. Kip won a science writing award for that book. This is a more general book about relativity and black holes, wormholes and all of that stuff, but there's a little bit about gravitational waves in there and space-time in general that's probably useful. There's a few links to my blog and various things for LIGO and Lisa. If you would like to participate with us, so we have participatory science programs, what's generally known as citizen science programs. There is a program that we have developed in collaboration with the Adler Planetarium and our colleagues at Syracuse called Gravity Spy. We show you actual data coming off of the LIGO detectors, and then we ask you to tell us what you're looking at. And most of these are not gravitational wave signals. We take them, we show it to the computer, and we say, see, not these. And then it learns how to do things better. Okay, so those of you who are familiar with Zooniverse, this is classic image matching. And so those of you with 8 and 9 year olds, they probably do this. My daughter's done 8 million more of these than I have. But it's easy to do while you're riding the bus to work or, sitting around on your lunch break, classify 5 spectra for us. So. Yeah, right. Yeah. So the nanograph folks also do this sort of stuff as well. Yeah, exactly. Okay. Yeah, so that's all I'm going to say. I'll say thank you, and I'll take questions for as long as we've got to answer questions. So, yeah. Okay. And Barbara, if someone online can speak up, if there's questions online, I'll answer those too, but I'll take this one from Doug to start with. So gravitational wave detectors are broadband detectors. And so we are sensitive to signals across the entire frequency band. And so one of the easiest ways to see them is to build spectrograms like the ones that you're seeing there. And then you can isolate just very narrow parts of the band and look for signals in the very narrow bands. Yeah. Okay. And so we have to do that by building filters that just pull out parts of the band. Yeah, that's right. Yeah. Yeah, that's right. And so the problem with nanograv is the wavelengths are years long. And so nature is going to give you whatever it gives you. So there's no guarantee you're near the top. With Lisa, right, we just have to wait 1,000 seconds and we're on a different part of the wave, right? So we have a little bit more freedom than the nanograph folks do. Yeah. Okay. Other questions, John?
And Shane, would you mind repeating the questions for?
Yes, I can do that.
Yeah, thank you.
Yes. Sorry, I will do that. So go ahead, John. Yes. Yeah, yeah, yeah. Okay, so the question is about how the cubes play a role in the game, how they are mirrors. And so what we do is we bounce the laser beam off the cube locally to know where it is, and then we send it out down the beam, and it hits the other cube, and then it measures how long did that take. Okay, and we do that both directions on each of the 3 arms, so there's 6 links. Yeah, yeah. Okay. Yes. Yes. Yeah, so each spacecraft has 2 cubes. There's 2 telescopes in each spacecraft. Yeah, yeah. And the question was, is the cubes are square, but the constellation's triangular. So what do you do about that? The other solution is to put 2 spacecraft at each corner. But Lisa is 1 spacecraft. So. Mhm. So the cubes are inside the spacecraft and not attached to anything. Let me see if I have a slide showing this. Sometimes I have a picture of this. Let's see here. Whoops, no, this one. So this is a movie. Let's see if I can get to the.
Oh,
Nope,
while you're
sorry, I
doing
thought
that,
it was in this movie. Okay, so yeah, so down inside the spacecraft there, it's not going to show it in the movie. There is a canister, and the canister is even better vacuum than the vacuum of space, which is why it's inside the canister. That's to keep dust and all kinds of stuff off of it. And then the cubes float right in the middle. So we clamp the cubes down, and then we push them out and we let them go, and they float inside a little chamber with just about a millimeter gap between the sides. And that's what it does. No, it sits there and it floats. And if gravity tells it to move, the spacecraft follows it. That's the point. It doesn't move anywhere except unless gravity tells it to go. So the spacecraft and the cubes are basically following the same orbit. And the gravitational waves make it kind of move a little bit, but not so much that the spacecraft has to do anything. But what we have to worry about is the solar wind, for instance, or the brightness from the sun pushes on the spacecraft and is trying to push the spacecraft this way, and the cube wants to go this way. So the spacecraft has to push itself back against the solar wind and keep following the cube. Those of you, anyone play robotics? You build robots? Okay, so the game here is just like the game you play if you try to build a balancing robot. It's the same kind of feedback loop that building a balancing robot, right? So when you're building a balancing robot, you want to tip over and you have to sense that. And the response has to be to move the robot's body back to vertical. So this is the same game. The spacecraft can tell, oh, I'm drifting this way. And the response has to be, I have to recenter myself on the cube. So if you go study balancing robots, it's kind of the same kind of technology. PIDS, as we call it. So the cube goes wherever, the spacecraft follows. That's right. Yeah. Okay. Up there in the back. Mm-hmm. Yeah. Okay. Okay, so the question is about the interference, as we would call it, of waves adding together constructively or destructively, right? And so the analogy to keep in mind here is really the analogy with sound, right? You and I can sit here in this room, and no matter how much we talk at each other, even though we're both talking in the same frequency band, and even if we were saying the same words back and forth, we would not be able to cancel each other out. And that's because the complexity of the signal you're generating compared to the complexity of the signal I'm generating are not exactly the same. When we learn about it's not, the waves absolutely add together, right? But to get them to effectively and coherently destructively interfere or constructively interfere is only really something that works when you have waves that are nearly identical. And when we teach you about that in physics class, we teach you using waves that are nearly identical. We build a wave generator over here and a wave generator over here. They're exactly the same. But in astrophysics, no two star systems are the same. They're not at exactly the same phase in their lives. They're not doing exactly the same thing. And so getting a perfect cancellation means we're in exactly the right spot at the right time. It's statistically improbable, right? Okay. Astronomically improbable, yes. So. Yes. All right, just a sec. Are there any questions online? Are we okay, Barbara?
There are questions online. Let me actually, by the way, ask the people online to use the dedicated Q&A section to ask their questions, because it's quite hard to track the questions on chat. Now, the question, the first question is about dark matter. Will LISA help dark matter research?
So yeah, so the answer to that is it depends on what the dark matter is. So I can do the dark matter talk for you all sometime, but one of the kind of defining features of dark matter right now is we don't know what it is. And in as much as the people who study WIMPs want us to believe it's WIMPs, there has been a resurgence in what are called machos, which are compact astrophysical objects being the dark matter. And a lot of that resurgence has come about because of the recent LIGO gravitational wave results, because LIGO has uncovered a different population of black holes than we expected 10 years ago. And so there's been a lot of deep thinking going on about whether or not a substantive fraction of the dark matter could be these kind of bigger black holes than were expected that LIGO's detecting. So that's one aspect of it. But the other aspect of it is that by definition, dark matter is matter. It interacts via gravitational interactions. And so if it was clumpy in any way, then it could in principle emit gravitational waves. And whether or not those gravitational waves are detectable by LISA or LIGO is really just a function of the clumping. And so if we saw gravitational waves with LISA, or we saw gravitational waves with LIGO that we thought came from some unknown clumpiness of something, that would be something that would be an indicator, a pointer that would lead us down the pathway to trying to understand what the dark matter might be. Whether or not that's likely or not, you know, you can pick as many physicists as you want to ask, and you'll get as many answers as people you ask. So we'll see. Our job as scientists is just to look and consider the possibilities.
Thank you. The next question is about white holes. Can LISA be used to prove the existence of white holes?
Yeah, so white holes, so those of you who don't know about, so if you write down the complete mathematical description for a black hole, it is possible that there are tunnels through black holes. Okay, so you go in through what's called the event horizon, that's our side, you fall in, you can't get back out. But if you go through the tunnel, you come out on the other side in what's called a white hole. And there's lots of arguments among gravitational physicists, which is my field, about whether or not these things are likely and whether or not nature closes off those tunnels. But our job as astronomers is not to say yes or no, it's to say we've looked or we haven't looked. And so in astronomy, we think very often about what we could look for that would be a signature of a white hole. A big bright source in the sky of all the junk coming flying out of a white hole, that's an observational thing you could do with telescopes. With gravitational waves, that's a very interesting question, because you know, the white hole in some sense is is mathematically similar to the black hole. And so you could imagine if it was in orbit around another object, that it wouldn't necessarily look any different in terms of gravitational waves than the black hole does. So I think it's unclear in my mind whether or not gravitational waves could tell you something definitive or not. The way it really probably would have the most impact is in this tests of general relativity that we were talking about earlier with the Emorys. If we really are supremely confident that the black holes are the black holes that general relativity predicts, then that means we have to be very supremely serious about the mathematical predictions, which include, for instance, things like white holes. So. Yes,
Thank
here in the
you.
audience.
And one more
Oh.
question before you.
Okay,
wanna
one
switch.
more, and then I'll go back to the room here.
Yes. About the orbit of LISA, is it, you mentioned it's orbiting the sun with the Earth, so is it on the L1 point?
It is not at the L1 point. So those of you who study orbits, you'll know there's these 5 balancing points around any 2 objects. So the Earth and the sun, for instance, or the Earth and the moon, called Lagrange points, and they're numbered L1, L2, L3, L4, L5. So it is not at one of the Lagrange points. The Lagrange point is 60 degrees behind or 60 degrees in front of the Earth in the Earth's orbit, and LISA is only 20 degrees behind the Earth. So it's not all the way to the Lagrange point. The reason we did that is it's far enough away that the gravitational perturbations from the moon aren't a problem, but it's close enough that we can talk to it with a radio telescope from the Deep Space Network. So, okay, here in the audience. It is most sensitive directly above and below the constellation. So the question is, does LISA point, basically? Yeah. So it's most sensitive above and below, but just like your ears, it's omnidirectional. So you're more sensitive to things in front of you than you are behind you, but you can hear things behind you nonetheless. Above and below, above and below. Yeah. Yeah, because that's like the grid that I showed you, right? Yeah. Mm-hmm. Yeah, so the question is about the cube and the structures you can see on the cube. So the corner structures are part of the clamping. So that's just the clamp points so that we don't touch the optical surface. The way we know where the cube is that when it drifts too close to one of the sides, we can capacitively sense that it's getting close to us. And so it's done passively with capacitance. Okay, and we're monitoring its position with the lasers, right? So we can tell it's moving away from us with the lasers if it were to start moving really fast in one direction. So, and one of the things, so this is one of the things we studied on Pathfinder is, you know, the cube will get out of whack. The spacecraft will do something weird, a thruster will go off, you know, something will happen, and we'll have to clamp. We call it caging. We clamp down on the cube again, and then we have to just start over from scratch again. So that absolutely happens, but we kind of count on it being where we leave it in the center of that cage. So the question is the laser signal pulse? No, it's continuous wave. So this is, I think it's 2 watts now, but traditionally we think of it in terms in 1 watt, continuous wave, 10 years. Yeah. Okay, one more. Yeah. Yeah. So the question is whether or not LISA will be sensitive to primordial gravitational waves. So inflationary era gravitational waves. Yeah. Yeah. So something beyond the cosmic microwave background, right? So if you look at the spectrum graph that I showed you, those waves, they're full spectrum. They occur at low frequencies, high frequencies all across. And the question is are they ever strong enough for LIGO, LISA, pulsar timing, anyone to detect? The standard, as we call it, slow rolling phasing gravitational waves at the current limits are below LISA's ability to detect. But Neil Cornish and I, very early on in my career, we wrote a paper about using LISA or LISA-like detectors to look for these primordial gravitational waves. And the simple fact of the matter is we don't know what the dark matter is and what the dark energy is. And so there are still exotic cosmological gravitational wave models that will produce signals that are strong enough to be detectable in this band that LISA observes in. So part of that is what's nature doing? We still don't know. And then part of it is the detector going to be sensitive enough? And so LISA may be sensitive enough, but if we build two LISAs and fly them together, and that's not an unrealistic possibility. The Chinese are working on one that in principle could be contemporary with LISA, then we could do that gravitational wave experiment that Neil and I wrote about. So. Well, we could be lucky. That's right. Because we just don't know enough about the universe because 97% of it's the stuff we don't know what it is, right? Yeah, that's right. So, okay, I'm going to wrap it up there. I'm happy to chat with anyone who wants to ask me more questions later. Certainly, thank you for all the questions and your attention, and I hope you all have a great evening.
Thank you. What a great talk.
Thanks.
Can we get the PowerPoint presentation?
Yeah, absolutely.
Oh, wonderful. Great. Thank you.
And
Thank you so
one
much.
thing, because there are a lot of good questions online remaining, Shane, you agreed to answer questions via email, right? Shane, can you hear me?
Yes, we can do that.
Yes.
Okay, so to all the people online whose questions remain unanswered, I apologize. We're just running out of time, and there's so many questions that we can't get to them possibly. So Shane was gracious enough to agree to answer to all your questions via email. So feel free to email him. You could find his email address on our website and also on his website. If you go to the calendar entry related to today's talk, quite a few questions were already answered, but there are some remaining. Okay, so I really appreciate you, Shane, and also joining us in person. That was great. Thank you very much. And I hope we could have you back at future to update us about the mission and also the other talks that you mentioned that you do.
Good.
Okay.
Yeah, I'm good. Yeah, thank you.
Great, sure. So if there is nothing else from any of the board members, we're ready to adjourn the online portion. I wish everybody best of luck. Please check our calendar at ocastronomers.org for the future events. And I'll see you all at the next meeting. Bye-bye now.